Hey everybody. Today we're doing a goodness of fit test example. We have a list of 41 digits between 0 and 9, and we'd like to know whether it's plausible that they might be randomly generated. Alternatively, is there evidence that they were made up by a human? We'll test at significance level alpha equals 0.05. It might be fun as you're watching this to take a guess. What do you think? Were these randomly generated or made up by a human? In order to test this, we're going to leverage the fact that humans tend to underestimate the frequency with which subsequent random digits are identical or even adjacent to one another. For us, it just feels like 1, 1, 1, 1 and 1, 2, 3, 4 aren't random, even though they're just as probable as any other four-digit sequence. For a truly random string of digits between 0 and 9, subsequent values are going to be identical to one another 10% of the time on average. They'll differ by 1, 20% of the time on average. And they won't be either of those things 70% of the time on average. I'm calling that being far away from one another. To keep things simple here, I'm considering the digits 0 and 9 to be adjacent to one another, to differ by 1, as if they were on the face of a clock. The alternative hypothesis here is just going to be that the string of random digits is not randomly generated and therefore does not have this frequency breakdown. Since there are 41 digits in our list, there are 40 pairs of values. If we go through that set of 40 pairs and count the number that are identical, differ by 1, and that are far apart, we find 1, 3, and 36 respectively. On the other hand, if the sequence of digits really is randomly generated, we expect to have 4 the same, 8 adjacent, and 28 far away. There I'm doing 10%, 20%, and 70% of 40, respectively. The chi-squared test statistic measures how far the observed counts are from the expected counts overall. We compute this by taking the observed count, subtracting off the expected, squaring that, and then dividing by the expected, doing that across all three categories, adding up those results. For instance, in that same category, we do 1 minus 4 squared divided by 4. Adding all those up, we get 7.66. We are going to use that test statistic to compute a p-value. We're going to do that in the distribution chi-squared of 2. The chi-squared distribution with 2 degrees of freedom, where 2 is 1 less than the number of categories, 3 in this case. For a chi-squared goodness of fit test, we always want a right-tailed probability because larger chi-squared values represent data that is further away from what we would have expected when the null hypothesis is true. I've drawn a picture here showing the area that we're trying to compute representing that probability. We compute a right-tailed probability by doing 1 minus the left-tailed probability, so using the cumulative distribution function of chi-squared of 2. You should always do that using technology. I use R where the command is p chi-squared. So the p-value is going to be 1 minus p chi-squared, 7.66, the test statistic we found, comma 2, the number of degrees of freedom in our chi-squared distribution. When we do that, we get a p-value of 0.022. Again, that's the probability of randomly getting a test statistic as large or larger than the one we actually observed when the null hypothesis is true. That is, when the digits are randomly generated. Since this p-value is less than the significance level that we set at the beginning of this problem, alpha equals 0.05, we reject the null hypothesis. And this data does represent good evidence that the list of numbers is not random.